Yo, experimental music, what the hell is that? Like a grown man rocking pigtails in the back. And that's a compliment, just being honest. Soundtrack to the rest of the shit I'm talking. Said experimental music, what the hell is that? Like a grown man rocking pigtails in the back. And that's a compliment, just being honest. Soundtrack to the rest of the shit I'm talking. And now it's time to cut the ribbon. The mystery of rap that's meta in description. The first rule of meta rap, no explicit mention. Illusion is the only form to give it recognition. Experimental music, what the hell is that? Like a grown man rocking pigtails in the back. And that's a compliment, just being honest. Soundtrack to the rest of the shit I'm talking. I said experimental music, what the hell is that? Like a grown man rocking pigtails in the back. And that's a compliment, just being honest. Soundtrack to the rest of the shit I'm talking. Try to make my mama proud, turned out I ain't shit. Spent my early years trying to get someone to pay attention. Finally learned that the thing you search for is in the searching. Unpredictable trajectory in this dimension. And the more I tried to grasp it, the further that it went. By the time I thought I got it, it left as fast as it came. As a kid I had a passion for listening to things. My first words, experimental music, what the hell is that? Hell is that? Hell is that? Hell is that? Like a grown man rocking pigtails in the back. And that's a compliment, just being honest. Soundtrack to the rest of the shit I'm talking. Said experimental music, what the hell is that? Like a grown man rocking pigtails in the back. And that's a compliment, just being honest. Soundtrack to the rest of the shit I'm talking. I was a curious kid with nothing to lose. Imagination ran wild with colorful views. Full of ambitions and dreams and wonderful hues. I think of everything I did to come up.
Introductory meta course for the J.O.L.A.L.F likely refers to a foundational program designed to introduce individuals to the core concepts and principles of the J.O.L.A.L.F framework. Without knowing the exact meaning of the acronym J.O.L.A.L.F, it's difficult to be more specific. However, generally, a meta course implies it's a course about courses, or a course about the underlying structure of a subject. Meta fundamentally implies a self-referential quality, where something reflects upon itself or its own classification. In creative contexts, it signifies a self-awareness within the work, acknowledging its constructed nature. Beyond this, meta describes a higher-order analysis, scrutinizing the foundational principles of a given topic. It can also represent a viewpoint that surpasses the immediate subject, offering a broader perspective. In computing and online environments, meta often pertains to data that describes other data, or information about information. Finally, in gaming, it has evolved to describe the most effective strategies and tactics currently prevalent. Case study, meta in film criticism. A film critic analyzes the movie being John Malkovich. They don't just review the plot and acting. Instead, they examine how the film uses its own medium to explore the nature of identity and storytelling. They discuss how the film's self-aware humor and bizarre premise draw attention to the artificiality of cinema itself. This critic is engaging in meta-analysis, going beyond surface-level interpretation to understand the film's commentary on the art of filmmaking and the construction of reality. They're examining the meta aspects of the film. In science, meta often denotes a higher-level analysis of existing research, as seen in meta-analyses that synthesize findings from multiple studies. A meta-study, for example, doesn't conduct new experiments but instead examines the overall trends and conclusions of previously published research. This approach allows scientists to identify robust patterns and reduce the impact of individual study biases. Meta-science, a related field, investigates the scientific process itself, aiming to improve research methodologies and reproducibility. This includes studying how research is conducted, funded, and published, to identify and address systemic issues. Essentially, meta in science represents a critical, reflective examination of the scientific enterprise. Case study: a team of researchers conducts a meta-analysis of 50 studies on the efficacy of a new antidepressant. Instead of running their own trials, they compile and statistically analyze the data from the existing studies. This meta-analysis reveals a small but significant overall positive effect of the drug, which wasn't apparent in many of the individual studies due to smaller sample sizes. This exemplifies how a meta-approach in science can provide a more comprehensive and statistically powerful understanding of a research question. Meta-theory is the study of theories themselves, examining their underlying assumptions, structures, and validity. It involves analyzing the language, concepts, and methodologies used within a theoretical framework. Meta-theorists seek to understand how theories are constructed, how they relate to each other, and how they contribute to our understanding of the world. It often involves questioning the epistemological foundations of knowledge claims made by specific theories. This examination can lead to the development of new theoretical perspectives or the refinement of existing ones. Ultimately, meta-theory aims to provide a more comprehensive and critical understanding of the nature of theory itself. Case study: a sociologist studying different theories of social inequality examines the underlying assumptions each theory makes about power, class, and individual agency. Point 1. This analysis, a form of meta-theory, reveals how each theory's perspective is shaped by its initial assumptions, influencing its conclusions. By comparing and contrasting these theoretical frameworks, the sociologist identifies commonalities and divergences, ultimately developing a more nuanced understanding of how social inequality is conceptualized. This meta-theoretical approach allows for a critical evaluation of the strengths and limitations of each theory, contributing to a more comprehensive understanding of the complex issue of social inequality. Syllabus, course goal: develop a rigorous understanding of meta as a recursive, higher-order analytical construct. Module 1, Foundational Meta-Concepts. Objective: define meta within a formal systems framework. Activities: analyze etymological origins via linguistic recursion. Formalize definitions using set theory and type theory. Apply reflexive analysis to personal cognitive models. Synthesize a formal definition of meta via logical deduction. Resources: formal logic texts. Type theory and set theory resources. Module 2, Meta-narratives in creative media. Objective: deconstruct meta as a semiotic and structural device. Activities: perform semiotic analysis of meta-elements in media. Apply structuralist and post-structuralist frameworks to narrative analysis. Deconstruct fourth wall breaches as instances of self-referential signification. Construct a meta-narrative using reflexive techniques. Resources: semiotics and narratology texts. Post-structuralist theory. Module 3, Meta-analysis and meta-science. Objective: understand meta as a statistical and epistemological tool. Activities: apply statistical methods to meta-analysis of research corpora. Analyze epistemological foundations of meta-science. Evaluate metadata structures in scientific data sets. Perform a methodological critique of a scientific research paradigm. Resources: statistical analysis texts. Philosophy of science journals. Module 4, Meta-theoretical frameworks. Objective: examine meta as a second-order theoretical construct. Activities: apply critical theory to analyze theoretical assumptions. Deconstruct theoretical frameworks via epistemological critique. Compare and contrast meta-theoretical paradigms. Construct a meta-theoretical model of a given theoretical system. Resources: critical theory and epistemology texts. Comparative theory resources. Module 5, Metadata and Metagaming. Objective: explore meta within digital and game theoretic contexts. Activities: analyze metadata schemas and data lineage. Apply game theory to strategic meta-analysis of competitive systems. Evaluate the sociological implications of metaverse architectures. Analyze the impact of recursive online phenomena. Resources: data science and database theory resources. Game theory and digital sociology texts. Assessment: formalized conceptual definitions. Structuralist and semiotic analyses. Statistical meta-analyses and epistemological critiques. Meta-theoretical model constructions. Digital systems analyses and game theoretic evaluations. It is possible to be a metaphysician without believing in a transcendent reality, for we shall see that many metaphysical utterances are due to the commission of logical errors, rather than to a conscious desire on the part of their authors to go beyond the limits of experience. J.O.L.A.L.F. The word meta has a rich and layered history, tracing its origins to the ancient Greek preposition and prefix meta mu epsilon tau. This seemingly simple word carried a surprisingly broad spectrum of meanings, encompassing concepts such as after, beside, with, among, and beyond. This inherent flexibility in its semantic range has allowed meta to evolve and adapt across various domains of thought and language throughout history. In its earliest usage, meta functioned primarily as a preposition, indicating a spatial or temporal relationship. A prime example of this is found in the term metaphysics. While we now associate metaphysics with profound inquiries into the nature of reality, its original meaning was far more prosaic. The title metaphysics was given to a collection of Aristotle's works that were placed after the physics in the ordering of his writings. It was a simple organizational marker, not a philosophical designation. However, as philosophical thought developed, the term meta began to acquire a more abstract and nuanced meaning. It began to signify a movement beyond or transcending the immediate subject matter. This is particularly evident in the evolution of the concept of metaphysics itself. From a mere organizational label, it transformed into a field of inquiry that sought to explore the fundamental principles of existence, going beyond the realm of physical phenomena. Case study: Aristotle's writings, initially organized after the physics metaphysics, illustrate meta's original spatial temporal function. Over time, metaphysics shifted from a simple organizational label to represent inquiries beyond the physical, exploring fundamental reality. This case demonstrates meta's linguistic evolution from a positional marker to a term signifying abstract, higher-level philosophical inquiry. A meta-language is, fundamentally, a language used to describe another language, which is called the object language. This concept is crucial for understanding how we analyze and discuss language itself, moving beyond simply using language to communicate about the world. Instead, a meta-language allows us to examine the structure, rules, and properties of language as an object of study. The need for a meta-language arises from the inherent limitations of using a language to describe itself. If we were to use English to define all the rules of English, we would inevitably encounter circularity and paradoxes. Therefore, a separate, higher-level language is necessary to provide a clear and unambiguous framework for describing the object language. This distinction is vital in fields like linguistics, logic, and computer science. In linguistics, meta-languages are used to describe the grammar, syntax, and semantics of languages. For example, linguists might use a formal meta-language to define the rules of sentence formation in English, specifying the relationships between different parts of speech and the permissible combinations of words. Similarly, in logic, meta-languages are used to define the rules of inference and the properties of logical systems. Logicians use meta-languages to talk about the validity of arguments and the consistency of formal systems. Computer science heavily relies on meta-languages for defining programming languages and data structures. For instance, Backus-Naur form BNF is a meta-language used to describe the syntax of programming languages, specifying the valid sequences of symbols and keywords. Similarly, XML schema is a meta-language used to define the structure and content of XML documents. These meta-languages enable computer scientists to create precise and unambiguous specifications for programming languages and data formats. The concept of a meta-language extends beyond formal systems. In everyday language, we often use meta-language implicitly when we talk about language itself. For example, when we say the word dog is a noun, we are using English as a meta-language to describe a specific aspect of English. However, in formal contexts, the distinction between the object language and the meta-language is made explicit to avoid ambiguity and to ensure clarity. The use of meta-languages is essential for rigorous analysis and precise communication about language. It allows us to step outside the language we are studying and to examine its properties from a higher-level perspective. Without meta-languages, our understanding of language would be limited to its use as a tool for communication, rather than as an object of study in its own right. Meta-languages provide the necessary tools for formalization, abstraction, and critical analysis of language systems. Case study: Backus-Naur form BNF in programming language definition. BNF is a meta-language used to define the syntax of programming languages like Python or C++. Instead of using English to describe the rules of how to write code which would be ambiguous, BNF provides a formal, precise way to specify the allowed combinations of symbols, keywords, and structures. For instance, BNF can define that an if statement must begin with the keyword if, followed by a condition within parentheses, and then a block of code. This meta-language ensures that compilers and interpreters can accurately parse and execute code, demonstrating how a meta-language enables clear and unambiguous communication about the structure of a programming language. The philosophy of meta delves into the nature of self-reference, abstraction, and the hierarchical structures of thought and reality. It grapples with the implications of systems that reflect upon themselves, and the paradoxes that arise from such recursive operations. At its core, the philosophy of meta questions the very foundations of knowledge and representation. One key aspect of this philosophy explores the limits of representation. When a system, be it a language, a theory, or a consciousness, attempts to describe itself, it often encounters inherent limitations. This is because the act of representation requires a separation between the representing and the represented, a distinction that becomes blurred in self-referential systems. This leads to questions about the possibility of complete self-knowledge and the nature of objective truth. Relatedly, the philosophy of meta examines the concept of levels of abstraction. It recognizes that reality can be understood at multiple layers, with each layer providing a different perspective. For example, we can examine a sentence as a string of words, as a grammatical structure, or as a vehicle for conveying meaning. The philosophy of meta seeks to understand the relationships between these different levels and the implications of moving between them. This exploration often involves the concept of emergence, where higher-level phenomena arise from the interaction of lower-level components. Furthermore, the philosophy of meta engages with the paradoxes that arise from self-reference. Classic examples include the liar paradox, the sentence is false, and Russell's paradox concerning sets that do not contain themselves. These paradoxes challenge our fundamental assumptions about logic and language, and force us to reconsider the nature of truth and consistency. The philosophy of meta attempts to understand these paradoxes, not simply as logical puzzles, but as fundamental insights into the limitations of our cognitive frameworks. The philosophy of meta also intersects with discussions about consciousness and artificial intelligence. The ability of a system to reflect upon its own processes is often seen as a key characteristic of consciousness. The question of whether machines can achieve true self-awareness hinges on our understanding of metacognition and the nature of subjective experience. Moreover, the creation of artificial intelligence raises questions about the ethical implications of creating systems that can manipulate and understand their own representations. Finally, the philosophy of meta extends to the exploration of the nature of theory itself. It involves reflecting on the assumptions, limitations, and biases inherent in our theoretical frameworks. This meta-theoretical approach seeks to improve our understanding of how knowledge is constructed and how different theories relate to each other. It acknowledges that all theories are ultimately representations, and that these representations are shaped by the perspectives and limitations of the theorists themselves. Therefore, the philosophy of meta encourages a critical and reflective approach to knowledge, recognizing that our understanding of reality is always mediated by our own cognitive and linguistic structures. Case study: Gödel's incompleteness theorems and the limits of formal systems. Gödel's incompleteness theorems, a cornerstone of the philosophy of meta, demonstrate the inherent limitations of formal systems. Like mathematics. 1 He proved that any sufficiently complex formal system contains statements that are true but cannot be proven within that system itself. This self-referential paradox, akin to the liar paradox, reveals that any system attempting to fully describe itself will inevitably encounter incompleteness. Gödel's work exemplifies the philosophical exploration of meta by showing how self-reference leads to fundamental limitations in knowledge and representation, highlighting the need to examine the system's meta level to understand its inherent constraints. Metabolism encompasses the entire set of chemical reactions that occur within an organism to sustain life. It's a complex and intricately regulated network of processes that break down nutrients to produce energy, catabolism, and build complex molecules for growth and repair, anabolism. These reactions are essential for everything from cellular maintenance to physical activity. At the core of metabolism lies the concept of energy transfer. Organisms acquire energy from their environment, typically in the form of food or sunlight. This energy is then converted into a usable form, primarily adenosine triphosphate ADP, which acts as the cellular energy currency. ADP powers various cellular processes, including muscle contraction, protein synthesis, and active transport. Catabolism involves the breakdown of complex molecules, such as carbohydrates, fats, and proteins, into simpler ones. This process releases energy, which is used to generate ADP. For example, the breakdown of glucose through glycolysis, the citric acid cycle, and oxidative phosphorylation yields ADP. Similarly, the breakdown of fatty acids through beta oxidation and the breakdown of proteins into amino acids also contribute to energy production. Anabolism, on the other hand, involves the synthesis of complex molecules from simpler ones. This process requires energy, which is supplied by ADP. Examples of anabolic processes include protein synthesis, DNA replication, and the synthesis of complex carbohydrates and lipids. These processes are crucial for growth, repair, and the maintenance of cellular structures. Metabolic pathways are tightly regulated by enzymes, which are biological catalysts that accelerate chemical reactions. These enzymes are subject to various control mechanisms, including feedback inhibition, allosteric regulation, and hormonal control. These mechanisms ensure that metabolic processes are coordinated and responsive to the organism's needs. The efficiency of metabolism can vary significantly between individuals and is influenced by factors such as genetics, age, sex, and physical activity level. Basal metabolic rate (BMR) represents the minimum amount of energy required to sustain life at rest. Factors such as muscle mass, body size, and hormone levels affect BMR. Metabolic disorders arise when there are disruptions in the normal metabolic pathways. These disorders can result from genetic mutations, enzyme deficiencies, or hormonal imbalances. Examples include diabetes, phenylketonuria (PKU), and hypothyroidism. These disorders can lead to a range of health problems, highlighting the importance of proper metabolic function. Case study: Type 2 diabetes and insulin resistance. In type 2 diabetes, the body's cells become resistant to insulin, a hormone that regulates glucose uptake. This metabolic disruption prevents glucose from being efficiently converted into energy. As a result, blood glucose levels rise, leading to hyperglycemia. This case exemplifies a breakdown in metabolic regulation, showcasing how impaired insulin signaling disrupts the normal energy processing pathways and contributes to a chronic disease. Metadata, at its core, is data about data. It provides contextual information that describes, explains, locates, or otherwise makes it easier to retrieve, use, or manage data. While the data itself might be the content of a document, a photograph, or a database record, the metadata is the information that surrounds and supports that content. It acts as a set of descriptive tags or attributes, enabling users and systems to understand and interact with the data more effectively. The importance of metadata stems from its ability to organize and structure vast quantities of information. Without metadata, data becomes difficult to search, retrieve, and interpret. Imagine a library without a catalog. Locating a specific book would be a daunting task. Similarly, in the digital realm, metadata acts as the catalog, providing the necessary information to navigate and understand the ever-growing sea of data. Metadata can take various forms, depending on the type of data it describes and the purpose it serves. For example, metadata for a digital photograph might include information about the date and time the photo was taken, the camera settings used, the location where it was captured, and the photographer's name. Metadata for a document might include the author, title, publication date, keywords, and file size. Metadata for a database record might include the data type, length, and format of each field, as well as information about the relationships between different records. The use of metadata is essential in numerous domains. In library science, metadata is used to catalog books, journals, and other resources, enabling researchers and patrons to find relevant materials. In information retrieval, metadata is used to index and search web pages, documents, and other digital content. In data management, metadata is used to track the provenance, quality, and security of data, ensuring its integrity and reliability. In digital preservation, metadata is used to document the characteristics of digital objects, enabling their long-term storage and access. Beyond these specific applications, metadata plays a crucial role in enabling interoperability between different systems and applications. By providing a common language for describing data, metadata facilitates the exchange and integration of information across diverse platforms. This is particularly important in the era of big data, where organizations need to manage and analyze vast amounts of data from various sources. Case study: metadata in digital photography, EXIF data. When a digital photograph is taken, the camera automatically embeds EXIF exchangeable image file format metadata within the image file. This metadata includes details like camera model, date time, GPS coordinates, shutter speed, and aperture. This data allows users to organize photos by location or date, software to automatically adjust image settings, and forensic investigators to verify the authenticity and origin of images. This demonstrates how metadata transforms a simple image file into a rich source of contextual information, enabling diverse applications. Metamorphosis, a profound biological process, signifies a dramatic transformation in an animal's form and structure after birth or hatching. This process is not merely growth, it's a fundamental change in the organism's body plan, often involving significant alterations in its physiology, behavior, and ecological niche. It's a striking example of developmental plasticity, where an organism's phenotype is radically reshaped in response to internal and external cues. The most well-known examples of metamorphosis occur in insects and amphibians. In insects, metamorphosis can be either incomplete hemimetabolous or complete holometabolous. Hemimetabolous insects, like grasshoppers and dragonflies, undergo gradual changes through a series of molds, with each stage resembling a larger version of the previous one. Holometabolous insects, such as butterflies, moths, beetles, and flies, experience a more drastic transformation involving a larval stage, a pupal stage, and an adult stage. The larval stage is often specialized for feeding and growth, while the pupal stage is a transitional phase during which the larval tissues are reorganized into the adult form. Amphibians, such as frogs and salamanders, also undergo remarkable metamorphosis. The larval stage, typically an aquatic tadpole, possesses gills, a tail, and a specialized mouth for feeding in water. During metamorphosis, the tadpole develops lungs, limbs, and a modified digestive system, transforming into a terrestrial or semi-aquatic adult. This transformation is driven by hormonal changes, particularly thyroid hormones, which trigger the remodeling of tissues and organs. Metamorphosis is intricately regulated by hormonal signaling pathways. In insects, hormones such as juvenile hormone and ecdysone control the timing and progression of molting and metamorphosis. In amphibians, thyroid hormones play a central role in coordinating the complex changes that occur during the larval to adult transition. These hormonal signals interact with genetic regulatory networks, ensuring that the appropriate developmental programs are activated at the correct time. The evolutionary significance of metamorphosis is profound. It allows organisms to exploit different ecological niches at different stages of their life cycle. For example, the larval stage may be specialized for rapid growth and dispersal, while the adult stage is adapted for reproduction and long-distance movement. This separation of life stages reduces competition between juveniles and adults and allows for greater specialization. However, metamorphosis also carries significant risks. The dramatic changes in body structure and physiology require substantial energy expenditure and can make the organism vulnerable to predation or environmental stressors. The timing of metamorphosis must be precisely coordinated with environmental cues to ensure that the organism transitions into the adult stage at an appropriate time and place. Case study: butterfly metamorphosis, larva to adult transformation. A caterpillar larva specializes in consuming leaves for rapid growth. It then enters a chrysalis pupa stage where its larval tissues are completely reorganized. Driven by hormonal changes, the chrysalis transforms into a butterfly adult with wings for flight and a proboscis for nectar feeding. This drastic metamorphosis allows the butterfly to exploit a completely different food source and habitat compared to its larval stage, showcasing the ecological advantages of this developmental transformation. The intersection of meta and animal magnetism, while seemingly disparate, touches upon the history of scientific inquiry, the nature of perception, and the evolution of our understanding of biological phenomena. Animal magnetism, a concept popularized by Franz Anton Mesmer in the late 18th century, posited the existence of a universal fluid or force that permeated all living beings, and that imbalances in this fluid could lead to illness. Mesmer believed he could manipulate this fluid, using passes and other techniques, to restore health. The meta aspect emerges when we analyze the broader context of Mesmer's theories and their reception. Mesmerism, as it came to be known, was not merely a medical practice, it was also a social and intellectual phenomenon. It sparked intense debate among scientists, philosophers, and the public, raising fundamental questions about the nature of evidence, the power of suggestion, and the role of the observer in scientific inquiry. The legacy of animal magnetism extends beyond its immediate rejection by the scientific establishment. The concept of a subtle, pervasive force influencing living organisms continued to resonate in various forms, including spiritualism, hypnosis, and alternative medicine. The study of hypnosis, in particular, owes a debt to Mesmer's work, even though the underlying mechanisms are now understood in terms of psychological processes rather than magnetic fluids. Furthermore, the history of animal magnetism highlights the complex interplay between scientific theories, social beliefs, and individual experiences. Mesmer's charismatic personality and the dramatic nature of his treatments contributed to his popularity, even in the face of scientific skepticism. The phenomenon of mesmerism underscores the importance of critical thinking and the need to distinguish between subjective experiences and objective evidence. The meta-perspective also invites us to reflect on the evolution of scientific understanding. What was once considered a fringe theory can, in retrospect, shed light on aspects of human psychology and physiology that were not fully understood at the time. The study of placebo effects, for example, has become an important area of research in medicine, demonstrating the power of the mind-body connection. Case study: the Royal Commission and the meta-analysis of mesmerism. The French Royal Commission, tasked with investigating Franz Mesmer's animal magnetism, went beyond testing the therapy itself. They established controlled experiments, including blind trials, to isolate the effects of Mesmer's fluid from suggestion. Their finding that effects were purely psychological, not magnetic, became a meta-commentary on scientific methodology, emphasizing the importance of rigorous testing and the placebo effect, shaping future scientific inquiry. Metafluidity, a concept that extends beyond the literal, delves into the realm of adaptable, transformative, and self-referential systems. It signifies a state of being where structures, ideas, or processes are not fixed but rather dynamically responsive to their own internal logic and external influences. This fluidity operates on a higher level of abstraction, reflecting a capacity for self-modification and adaptation that transcends simple change. At the heart of metafluidity lies the notion of self-awareness. A metafluid system is not merely reactive, it possesses a degree of introspection, enabling it to monitor its own states and processes. This self-monitoring allows for adjustments and modifications based on internal feedback loops, leading to a continuous process of refinement. This concept finds relevance in various domains. In the realm of technology, metafluidity can be observed in adaptive algorithms and artificial intelligence systems. These systems are designed to learn and evolve based on their own performance, dynamically adjusting their parameters and strategies to optimize outcomes. They exhibit a form of self-referential adaptability, where their behavior is shaped by their own experiences. In the sphere of social systems, metafluidity manifests in the ability of organizations or communities to adapt to changing circumstances. This involves not only responding to external pressures but also reflecting on their own internal structures and processes. Metafluid organizations are characterized by their capacity for continuous learning, innovation, and restructuring. The concept of metafluidity also extends to the realm of thought and consciousness. It describes the ability of the mind to reflect on its own cognitive processes, to challenge its own assumptions, and to revise its own understanding of the world. Metafluid thinking is characterized by its flexibility, its openness to new perspectives, and its capacity for self-transformation. Furthermore, metafluidity can be observed in artistic expression. Modern and postmodern art often explores the boundaries of representation, blurring the lines between reality and artifice. These artistic movements exhibit a form of metafluidity, where the medium itself becomes a subject of exploration, and the relationship between the artist, the artwork, and the audience is constantly redefined. The concept of metafluidity also invites us to reconsider the nature of identity and existence. In a world characterized by constant change and flux, traditional notions of fixed identities and stable realities are challenged. Metafluidity suggests that identity and reality are not static entities but rather dynamic processes, constantly evolving and adapting to their own internal logic and external influences. Case study: Agile software development as metafluidity. Agile software development, unlike traditional waterfall methods, embraces change. Teams continuously reassess their processes and adapt to evolving requirements. Daily stand-up meetings allow for immediate feedback and adjustments. Sprints, short development cycles, enable rapid iteration. Retrospectives, post-sprint reviews, facilitate self-reflection and process improvement. This constant, iterative adaptation, driven by feedback and self-evaluation, demonstrates metafluidity in action, ensuring the software product dynamically evolves to meet the changing needs of the user. Metatopology and metatypology, while related, address distinct aspects of organizational and representational systems. Metatypology, as discussed, focuses on the classification of typologies themselves, examining the underlying principles and biases involved in creating categories. It analyzes how and why we create systems of classification, scrutinizing the criteria used to differentiate categories and the purposes these systems serve. Metatopology, conversely, delves into the higher-level study of spatial and relational structures. It investigates the overarching frameworks and principles that govern how elements are arranged and interconnected. It moves beyond the specific details of a particular topology to examine the fundamental characteristics of spatial organization, connectivity, and network structures. This involves abstracting from particular arrangements to identify general properties like connectivity, adjacency, and hierarchy. Where metatypology examines the what and why of classification, metatopology explores the how and where of arrangement. It investigates the underlying principles that govern the spatial or relational organization of elements, regardless of their specific content. Metatopology considers how elements are connected, how they relate to one another in space or network, and how these relationships influence the overall system. Both metatypology and metatopology are concerned with higher-order analysis, but their focus differs. Metatypology is about the classification of classification, while metatopology is about the structure of structure. In essence, metatypology examines the frameworks used to categorize things, and metatopology examines the frameworks used to arrange them. Case study: Network analysis of social media platforms. Metatopology versus personality type systems. Metatypology. Metatopology, analyzing how social media platforms like Twitter or Facebook are structured as networks, nodes as users, Edges as connections. A metatopology study would examine general network properties like degree distribution, clustering coefficients, and path lengths, regardless of the specific content shared. It focuses on the underlying network structure and how information flows. Metatypology, examining systems like the Myers-Briggs Type Indicator MBTI or the Enneagram. A metatypology study would analyze the criteria used to define personality types, the relationships between different types, and the validity of the underlying dimensions, e.g. introversion-extroversion. It focuses on the principles behind the classification system itself, not the traits of individuals within those categories. Metarealism, a philosophical stance, proposes that reality exists independently of our perceptions and beliefs, but acknowledges that our understanding of this reality is fundamentally shaped by our cognitive frameworks and representational systems. It avoids the extremes of naive realism, which assumes direct access to reality, and radical constructivism, which posits that reality is entirely a product of our minds. Instead, metarealism seeks a middle ground, recognizing both the objective existence of reality and the subjective nature of our knowledge. A core tenet of metarealism is the recognition of multiple, potentially valid, representations of reality. It acknowledges that different cognitive frameworks, cultural perspectives, and scientific theories can offer distinct, yet equally legitimate, ways of understanding the world. This does not imply that all representations are equally accurate or useful, but rather that our access to reality is mediated through these diverse lenses. Metarealism emphasizes the importance of critical reflection on our representational systems. It encourages us to examine the assumptions, biases, and limitations inherent in our cognitive frameworks, and to recognize that our understanding of reality is always partial and provisional. This critical self-awareness allows us to refine our representations and to move closer to a more comprehensive understanding of the world. Furthermore, metarealism acknowledges the role of intersubjectivity in shaping our understanding of reality. It recognizes that our knowledge is not solely a product of individual cognition, but is also shaped by social interactions, cultural norms, and shared experiences. This intersubjective dimension highlights the importance of dialogue, collaboration, and the exchange of perspectives in constructing a more robust understanding of the world. Case study: scientific models of the atom. Metarealism. Physicists developed various atomic models Bohr, quantum mechanical over time. 1 Each model, while based on empirical data and independent reality, reflects a specific theoretical framework and representational system. 2 Metarealism acknowledges each model's validity within its context, despite their differences, recognizing that they offer distinct, yet potentially useful, ways to represent an unobservable reality. The evolution of atomic models, driven by critical reflection and intersubjective dialogue, illustrates metarealism's approach, acknowledging an objective reality while recognizing the mediating role of human representation. Metasynthesis, a qualitative research methodology, involves the interpretive integration of findings from multiple qualitative studies to produce a new, overarching understanding of a phenomenon. Unlike meta-analysis, which focuses on statistical aggregation, metasynthesis seeks to synthesize the conceptual and theoretical insights from diverse qualitative research, leading to a richer and more nuanced interpretation. It involves a process of critically appraising, comparing, and translating findings across studies, identifying common themes and patterns while also acknowledging contextual variations and divergent perspectives. This approach aims to move beyond individual study findings to generate a more comprehensive and insightful understanding of complex social phenomena, contributing to theory development and informing practice. Case study: metasynthesis of patient experiences with chronic pain management. Researchers conducted a meta-synthesis of 10 qualitative studies exploring patient experiences with chronic pain management. They didn't simply summarize findings. Instead, they identified recurring themes like loss of control, negotiating identity, and seeking validation, while also noting variations based on cultural background and pain type. This meta-synthesis yielded a deeper understanding of the lived experience of chronic pain, informing the development of more patient-centered care models, a result unattainable from any single study. Within the context of chemistry, particularly in IUPAC nomenclature, meta functions as a prefix with specific applications. In organic chemistry, it denotes a 1,3 positioning of substituents on an aromatic ring, as exemplified by resorcinol. Additionally, meta can indicate a dehydrated form within a series of acids, salts, or organic compounds. This is illustrated by the formation of metabisulfite from bisulfite, or metaphosphoric acid from orthophosphoric acid. Similarly, meta-antimonic acid represents the dehydrated form of antimonic acid. Therefore, within chemistry, meta signifies positional relationships in aromatic compounds and dehydration processes, distinct from its broader philosophical or analytical usage. Case study: resorcinol formation meta-substitution. When benzene undergoes a double substitution reaction, and the two substituents attach to the aromatic ring at the 1,3 positions, the resulting compound is designated with the meta prefix. Resorcinol, a dihydroxybenzene with hydroxyl groups at the 1,3 positions, illustrates this. This precise use of meta in organic chemistry nomenclature distinguishes it from other possible substitution patterns ortho or para and accurately conveys the molecule's structure. Metatuples, in a computational context, represent tuples that contain other tuples as elements. This creates a hierarchical or nested structure, allowing for the representation of complex, multi-layered data relationships. Unlike simple tuples that hold atomic data types, metatuples provide a mechanism to group related tuples, forming a tuple of tuples. This is particularly useful for representing data with inherent groupings or substructures, where individual tuples represent specific entities or attributes, and the metatuple represents their relationships or aggregations. Metatuples can be used to model complex data structures, such as records with nested fields, or relationships between entities that have their own attributes. They provide a way to organize and access data in a structured and efficient manner, similar to how nested lists or dictionaries are used in programming. Case study: representing student course enrollment data metatuples. A student enrollment system uses metatuples to store data. Each student's enrollment is represented as a metatuple. The outer tuple contains the student's ID and a nested tuple. The nested tuple contains course ID, course name, and grade. This structure allows efficient retrieval of all courses taken by a specific student, along with their associated grades, demonstrating how metatuples effectively model hierarchical data relationships. A metaring, in the context of chemistry, specifically organic chemistry, refers to a benzene ring that has substituents positioned at the 1,3 positions relative to each other. This positional designation is crucial in distinguishing isomers of aromatic compounds. Unlike ortho 1,2 or para 1,4 substitutions, meta-substitution creates a distinct spatial arrangement of the substituents around the benzene ring. This arrangement influences the molecule's properties and reactivity. The meta prefix is used in the systematic naming of such compounds to clearly indicate this 1,3 relationship. The metaring structure is a specific example of arene substitution patterns, and its presence dictates how the molecule interacts with other chemicals. The designation is a core part of the IUPAC nomenclature, ensuring clear communication of molecular structure. Case study, metaxylene synthesis. When xylene dimethylbenzene is synthesized, if the two methyl groups attach to the benzene ring at the 1,3 positions, the resulting compound is specifically named metaxylene. This precise meta-designation differentiates it from orthoxylene 1,2 positions and paraxylene 1,4 positions, each having distinct chemical properties. The formation of metaxylene highlights the importance of the meta prefix in accurately describing and distinguishing specific aromatic isomers. Metamicroprocessing, a theoretical field, would represent a higher-level analysis of microprocessing architectures and operations, transcending the direct design of individual processors. It would involve developing abstract models and simulations to optimize existing designs, explore novel computational paradigms like neuromorphic or quantum computing, and create metacompilers for automated code optimization. This field would focus on understanding the fundamental principles of information processing at the micro level, seeking to improve efficiency and explore new frontiers beyond traditional von Neumann architectures, essentially studying how to study and improve microprocessors themselves. Case study, automated design space exploration for quantum microprocessors. Metamicroprocessing. Researchers develop a metamicroprocessing tool that uses abstract models to simulate various quantum microprocessor architectures. Instead of manually designing each layout, they define high-level parameters: qubit connectivity, gate operations. The tool then automatically explores the design space, evaluating performance metrics like gate fidelity and error rates. This meta-approach accelerates the discovery of optimal architectures for specific quantum algorithms, demonstrating how metamicroprocessing can optimize the design process itself. Quantum meta explores the application of meta-concepts to quantum mechanics, focusing on self-referential and hierarchical aspects of quantum systems. It involves developing meta-quantum algorithms for optimizing quantum computations, studying meta-quantum states that encode information about other quantum systems, and investigating the philosophical implications of self-referential quantum phenomena. This field also aims to create meta-quantum languages for higher-level manipulation of quantum information, ultimately seeking to deepen our understanding and control of quantum systems for advancements in quantum technologies. Case study, quantum error correction meta-algorithm development. Researchers develop a quantum meta-algorithm that analyzes the performance of various quantum error correction codes. Instead of manually selecting a code, the algorithm uses quantum machine learning to learn the optimal code parameters based on the specific noise characteristics of a quantum computer. This automated, meta-level approach significantly improves the reliability of quantum computations by dynamically adapting error correction strategies, demonstrating the practical application of quantum meta principles. Meta-correction involves a higher-level approach to error correction, focusing on the analysis and optimization of correction mechanisms themselves rather than directly correcting errors in the raw data. It encompasses the development of systems that assess, refine, and adapt error correction strategies based on the characteristics of the errors and the performance of the correction process, potentially employing machine learning or adaptive algorithms to improve the efficiency and effectiveness of error mitigation. This approach seeks to create self-improving error correction systems that dynamically respond to changing conditions and optimize their performance, leading to more robust and reliable data integrity. Case study, adaptive error correction in wireless communication networks. Meta-correction. A wireless network employs a meta-correction system that analyzes real-time error patterns and feedback from receivers. Instead of using a fixed error correction code, the system dynamically adjusts the code's parameters and even switches between different codes based on signal strength and interference levels. This adaptive approach minimizes overhead and maximizes throughput, demonstrating how meta-correction improves network reliability by optimizing the error correction process itself. Metateleology extends traditional teleological arguments by examining the underlying assumptions and frameworks that shape our understanding of purpose and design in the universe. It moves beyond specific instances of apparent design to analyze the very nature of teleological reasoning, exploring questions about the validity of attributing purpose to natural phenomena, the role of anthropomorphism in teleological explanations, and the implications of teleological thinking for our understanding of causality and natural laws. This higher-level analysis seeks to clarify the conceptual foundations of teleology, assess its limitations, and explore its potential contributions to philosophical and scientific discourse. Case study, analysis of the fine-tuning argument metateleology. Instead of arguing directly for a divine designer based on the fine-tuning of physical constants, a metateleological approach would analyze the argument itself. This includes examining the assumptions about probability, the definition of fine-tuning, the limitations of our understanding of alternative universes, and the potential biases in human perception that lead us to perceive design. This focuses on the structure and validity of the teleological reasoning, rather than the specific examples used to support it. The term meta-tuning, particularly in the context of in-ear monitors IEMs, refers to a recent trend in audio tuning that aims for a specific sound signature based on updated measurement standards. This new meta is largely derived from data collected using the newer B&K 5128 measurement rig, which provides more accurate readings, especially in the bass and treble regions. This tuning generally emphasizes a diffuse field target with a slight downward tilt and an enhanced bass shelf, seeking to replicate the sound of a well-treated listening room. Essentially, it represents an attempt to establish a new, more precise neutral sound signature for IEMs, though it remains a topic of ongoing discussion within the audiophile community. Case study, scrutinizing the fine-tuning argument's probabilistic assumptions. This case study focuses on a metateleological approach to the fine-tuning argument by rigorously analyzing its probabilistic foundations, encompassing the selection of probability distributions, the measure problem associated with unknown or infinite sets of universes, the inherent selection effect imposed by our existence, the validity of assuming independent physical constants, and the application of Bayesian reasoning to assess prior probabilities. By dissecting these assumptions, the study aims to demonstrate how variations in probabilistic frameworks can significantly alter the perceived strength of the fine-tuning argument, highlighting the crucial role of meta-analysis in evaluating complex philosophical claims. Meta-constants, in the context of the fine-tuning argument, are not the physical constants themselves, but rather the underlying assumptions and parameters used in the argument about those constants. These include the choice of probability distributions for those constants, the methods used to define the range of life-permitting values, the assumptions about the independence of constants, and the selection effects inherent in our observation of a universe capable of supporting life. Essentially, they are the abstract variables within the philosophical framework used to interpret and argue about the significance of the physical constants. Case study, sensitivity analysis of the life-permitting range in fine-tuning arguments. This case study examines the meta-constant of the life-permitting range within fine-tuning arguments by performing a sensitivity analysis. It investigates how varying the assumed boundaries of this range, often based on complex astrophysical models and assumptions about alternative biochemistries, affects the calculated probability of a life-supporting universe. By systematically altering these boundaries and observing the resulting changes in the argument's strength, the study reveals the critical dependence of fine-tuning conclusions on the subjective and often uncertain definition of life-permitting, thereby highlighting a key meta-constant that influences the argument's perceived validity. Meta in the context of the brain refers to cognitive processes that monitor, regulate, and reflect upon other cognitive processes. This encompasses metacognition, which includes awareness of one's own thoughts, knowledge, and learning strategies, as well as the ability to control and adjust these processes. It involves the brain's capacity to step back and analyze its own operations, enabling self-awareness, error correction, and strategic thinking. This meta-level of processing is crucial for higher-level cognitive functions such as decision-making, problem-solving, and conscious experience. Case study: Metacognitive deficits in frontal lobe injury and decision-making. This case study examines patients with frontal lobe injuries, focusing on the observed deficits in metacognitive abilities, specifically their impaired capacity for self-monitoring and error correction during complex decision-making tasks. By comparing their performance and self-assessment accuracy to healthy controls, the study demonstrates how frontal lobe damage disrupts the meta-level of cognitive control, leading to overconfidence, poor judgment, and an inability to adapt strategies, thus illustrating the crucial role of metacognition in effective executive function. Metaglass refers to a theoretical or conceptual material that possesses optical properties beyond those found in conventional glasses, often achieved through engineered microstructures or metamaterials principles. Unlike traditional glass, which is typically amorphous and isotropic, metaglass might exhibit properties like negative refractive index, perfect lensing, or invisibility cloaking. These properties arise not from the material's chemical composition alone, but from the precise arrangement of subwavelength structures within it, manipulating light in unconventional ways. The concept of metaglass explores the potential to tailor light-matter interactions at a fundamental level, opening possibilities for advanced optical devices and applications. Case study: experimental realization of a flat metalens using metaglass principles. This case study focuses on the development and testing of a flat metalens, designed using metaglass principles to achieve subwavelength focusing without the curved surfaces of traditional lenses. By fabricating a precisely patterned metasurface, acting as a metaglass, researchers demonstrated its ability to manipulate light wave fronts, achieving diffraction-limited focusing and imaging. This case study illustrates the practical application of metaglass concepts, showcasing the potential for compact and high-performance optical devices. The diagram depicts a linear meta process, where input is transformed into output through a cyclical process. A separate railroad diagram illustrates a flow control structure with conditional branching. This structure begins with a start state and evaluates a condition, leading to different actions. The diagram includes a loop, allowing for repeated condition checks and action executions. Finally, the process concludes at an end state, showcasing a complete flow. These diagrams are useful for visualizing linear processes and complex control flows. Case study: Graph LR. A linear meta-B process, BC input, BD transformation, BE output, CB, DB, EB, subgraph railroad diagram. F start G condition, GSH action 1, G no I action 2, HJ loop, IJ, J yes G, J no K end. Meta signifies a higher level analysis, examining the frameworks governing a concept rather than its content. Processing meta involves exploring the underlying structures and rules that shape understanding. It shifts focus from the subject itself to how it's presented and analyzed. This deeper examination reveals hidden assumptions and alternative perspectives. Applications span fields like philosophy, literature, and technology, fostering critical thinking. Ultimately, metaprocessing aims for a more profound comprehension and encourages innovation. Case study: Meta in literature. In literature, the concept of meta is exemplified in metafiction, a genre where the narrative self-consciously reflects on its own construction. A notable example is If on a Winter's Night, a Traveler by Italo Calvino. This book disrupts traditional storytelling by directly addressing the reader and drawing attention to itself as a work of fiction. Rather than merely presenting a story, it examines the act of reading, the structure of narrative, and the relationship between the author, text, and audience. By engaging in this higher-level analysis, if on a winter's night a traveler invites readers to question assumptions about storytelling and meaning, fostering a deeper comprehension of the literary process and inspiring innovative approaches in narrative construction. This demonstrates how metaprocessing shifts focus from the content, the story, to the framework, the act of storytelling itself. Synthetic meta refers to the deliberate and structured examination of how attention operates within a system or concept, emphasizing the interplay between focus, interpretation, and comprehension. It moves beyond merely observing attention to analyze the mechanisms and dynamics that guide where and how attention is directed. By applying synthetic meta in attention, we explore the frameworks that prioritize certain elements over others, scrutinize the biases shaping focus, and unravel the processes that facilitate deeper engagement. This approach reveals insights about the construction and management of attention, enabling more refined strategies to capture, sustain, and channel focus effectively, fostering innovation and critical thinking in various disciplines. Case study: Synthetic meta in digital advertising. In digital advertising, synthetic meta is applied to understand how attention is captured and retained within online platforms. For instance, algorithms on social media analyze user behavior to prioritize specific content in a feed. By examining these mechanisms, such as how visual stimuli, text, or interaction prompts draw focus, advertisers can refine strategies to optimize engagement. This structured exploration highlights biases, like favoring sensational content, and reveals methods to sustain attention, such as personalized recommendations. Applying synthetic meta here fosters innovation in attention management while encouraging critical evaluation of ethical considerations in digital attention economies. Meta-externalism is the philosophical view that understanding or meaning is not entirely determined internally but depends on external factors or contexts. It posits that the framework governing concepts, language, or knowledge is influenced by interactions with the environment, society, or external systems rather than being confined to the mind or isolated structures. By analyzing meta-externalism, one uncovers how external relationships and dynamics shape meaning, interpretation, and comprehension, emphasizing the interconnectedness between internal cognition and external reality. This approach broadens perspectives and fosters critical inquiry into the foundations of knowledge and communication. Case study: Meta-externalism in language. Meta-externalism can be observed in the way language evolves through societal interaction. For example, the meaning of the word cloud expanded from referring to weather phenomena to encompassing digital storage due to technological advancements and external societal shifts. This evolution demonstrates how external factors like innovations, cultural trends, and collective usage shape the framework and understanding of language. By examining this process, meta-externalism highlights the interplay between external contexts and internal cognition, offering deeper insights into how knowledge and communication are dynamically constructed. A metapragma is a directive or instruction that operates on the code or data itself, rather than the intended output of the code. It influences how the compiler, interpreter, or other processing tools handle the information. This can involve specifying optimization strategies, defining data structures, or controlling the generation of related files. The purpose is to provide instructions about the processing of the code, affecting its behavior or structure at a higher level. Metapragmas are often used to enhance performance, ensure compatibility, or automate certain development tasks. Case study: Metapragma in C++. In the C++ programming language, metapragmas are utilized to provide instructions that influence the compilation process at a higher level. A well-known example is the pragma directive, which allows developers to enable or disable specific compiler features. For instance, pragma optimize can be used to control optimization settings, tailoring performance improvements to specific sections of code. Another example is pragma pack, which adjusts the alignment and packing of data structures to reduce memory usage or ensure compatibility with external systems. By examining how these metapragmas function, developers gain insights into the mechanics of the compilation process, enabling them to optimize application performance, streamline memory management, and integrate seamlessly with other systems. This structured exploration highlights the interplay between code behavior and its underlying processing, demonstrating the practical and transformative potential of metapragmas in software development. Dynamic meta refers to the adaptive and responsive analysis of frameworks and systems that evolve in real time. It emphasizes the interplay between changing contexts, variables, and mechanisms, focusing on how these elements influence the behavior, structure, and outcomes of a system. By engaging in dynamic meta, one can examine the fluid and iterative processes that govern adaptability and innovation, uncovering insights into how systems or concepts remain effective amidst continuous change and external pressures. This approach is particularly valuable in fields like technology, ecology, and organizational management, where responsiveness to evolving environments is essential. Case study: Dynamic meta in autonomous vehicles. Dynamic meta is evident in autonomous vehicle systems, which analyze and adapt to real-time changes in their environment. For instance, self-driving cars use dynamic meta frameworks to integrate data from sensors, cameras, and GPS to assess road conditions, detect obstacles, and adjust their routes or speed accordingly. This continuous, higher-level processing allows the system to respond effectively to evolving situations, such as unexpected traffic patterns or weather changes, ensuring safety and efficiency. The dynamic meta approach highlights the importance of adaptability and responsiveness in achieving real-time operational success. Meta cybernetics involves the higher-level analysis of cybernetic systems, focusing on the frameworks and principles that regulate their feedback, control, and adaptability. It explores how cybernetic systems function, not just through their inputs and outputs, but by examining the mechanisms and contexts shaping their processes and interactions. By understanding the recursive and dynamic relationships within these systems, meta-cybernetics offers insights into improving their efficiency, adaptability, and responsiveness, and it provides valuable perspectives for designing systems that can evolve and self-regulate in complex and changing environments. Case study: Meta-cybernetics in healthcare systems. Meta-cybernetics is applied in modern healthcare systems, particularly in patient monitoring technologies. For example, wearable devices like smartwatches monitor vital signs such as heart rate, oxygen levels, and activity in real time. At a meta level, the systems analyze how these data points interact and provide feedback to both patients and healthcare providers, creating a loop of continuous adaptation. This higher-level analysis helps refine algorithms for better predictions, such as identifying early signs of cardiac events, and improves the system's responsiveness to individual needs, showcasing the power of meta-cybernetics in improving personalized healthcare outcomes. Meta-cloud refers to the abstraction and analysis of cloud computing, focusing on the frameworks and mechanisms that enable its functionality. It examines how cloud services are structured, managed, and integrated across platforms, exploring the interplay between data storage, computation, scalability, and accessibility. By adopting a meta-perspective, one can evaluate the underlying principles guiding cloud architecture, uncover hidden inefficiencies, and identify opportunities for innovation. This approach also highlights the role of external contexts such as global connectivity, environmental impact, and evolving user needs in shaping cloud technologies and their applications. Case study: Meta-cloud in multi-cloud strategies. Meta-cloud concepts are applied in the management of multi-cloud strategies, where businesses integrate services from multiple cloud providers like AWS, Microsoft Azure, and Google Cloud. By analyzing the frameworks that govern interoperability, data flow, and optimization across these platforms, organizations can uncover inefficiencies, such as duplicated workloads or excessive data transfer costs. This higher-level evaluation enables them to design unified management tools and strategies that streamline operations, improve scalability, and enhance performance. The meta perspective helps align cloud infrastructure with evolving business goals and external demands, driving innovation in cloud utilization. Meta scattering refers to the higher-level analysis of how particles or waves, such as light, sound, or electrons, scatter when interacting with a medium or surface. It goes beyond observing the scattering phenomena to examine the underlying structures, properties, and mechanisms that influence the scattering behavior. By focusing on meta-scattering, researchers can optimize materials, design systems for improved performance, and address challenges in fields like optics, acoustics, and quantum mechanics, leading to advancements in imaging, communication, and material science technologies. Case study: Meta-scattering in biomedical imaging. Meta-scattering is applied in advanced biomedical imaging techniques, such as optical coherence tomography (OCT). Researchers analyze how light scatters within biological tissues to improve image resolution and depth. By studying the structures and properties influencing scattering, such as tissue density and refractive index variations, scientists develop models to enhance clarity and accuracy in diagnosing conditions. This meta-level understanding drives innovations in imaging technologies, allowing for more precise visualization of complex biological systems. Meta-absorbance refers to the analysis of how materials or systems absorb energy, such as light, sound, or heat, by examining the governing mechanisms and frameworks rather than just the absorption itself. It explores factors like the structure, properties, and interactions of the material or system that influence absorption processes. This approach enables a deeper understanding of the dynamics behind energy absorption, uncovering opportunities for optimizing performance or innovating applications in fields like optics, acoustics, or thermal engineering. By focusing on meta-absorbance, one can address complex challenges and drive advancements in energy manipulation technologies. Case study: Meta-absorbance in solar panels. Meta-absorbance is evident in the design of advanced solar panels, where researchers analyze not only how light is absorbed but also the mechanisms influencing efficiency. For example, meta-analysis of nanostructured coatings examines how they enhance light trapping by reducing reflection and maximizing absorption across a broader spectrum. This higher-level approach informs innovations like anti-reflective surfaces and multi-layered materials, improving the panel's energy conversion efficiency while adapting to diverse environmental conditions. Meta-absorbance thus drives technological advancements in sustainable energy solutions. Meta-collision refers to the analysis of how systems, entities, or processes interact and converge at a higher level, leading to transformative outcomes or insights. It focuses on understanding the dynamics, frameworks, and principles governing these interactions, as well as their broader implications. This perspective highlights opportunities to optimize or innovate by leveraging the effects of these collisions, offering valuable insights in fields like technology, social systems, and scientific research. Case study: Meta-collision in particle physics. Meta-collision is exemplified in particle physics experiments, such as those conducted at CERN's Large Hadron Collider. Scientists analyze high-energy collisions between particles to explore the fundamental properties of matter and energy. By studying the interactions and resulting phenomena, including the creation of new particles, researchers gain insights into the frameworks that govern the universe at its most basic level. This meta-level understanding drives advancements in theoretical physics and expands our comprehension of the cosmos. Meta-extremes refer to the analysis of systems, behaviors, or phenomena under extreme conditions or at their limits. This concept focuses on understanding how variables, frameworks, and interactions adapt or break down when pushed beyond conventional boundaries. By examining these extreme scenarios, researchers uncover insights into resilience, adaptability, and failure mechanisms, which are valuable for innovation and for preparing systems to handle unprecedented challenges effectively. Case study: Meta-extremes in aerospace engineering. Meta-extremes are explored in the testing of spacecraft materials, where conditions like extreme temperatures, vacuum environments, and high radiation are simulated. For example, NASA subjects thermal protection systems to intense heat during re-entry simulations to understand failure thresholds and resilience. By analyzing material behavior under these extreme conditions, engineers refine designs to ensure reliability and safety, enabling successful space exploration and operations in harsh extraterrestrial environments. Dehyphenated meta refers to the seamless integration and analysis of concepts without separating their components or breaking them into isolated elements. It focuses on understanding interconnected systems, frameworks, or ideas in a holistic manner, emphasizing the relationships and interactions within the whole structure. This approach is particularly useful in contexts where dividing elements might obscure the broader patterns or dynamics at play, fostering comprehensive insights and promoting innovative applications. Case study: Dehyphenated meta in ecosystem analysis. In ecosystem analysis, dehyphenated meta is applied to study the interconnected relationships between species, resources, and environmental factors holistically. Rather than isolating individual components like predator-prey dynamics or nutrient cycles, researchers examine how these elements work as a cohesive system. For instance, understanding the impact of climate change requires analyzing the interplay of temperature shifts, biodiversity, and resource availability together. This approach fosters comprehensive insights into ecosystem resilience and informs strategies for conservation and sustainable management. Meta-extelligence refers to the analysis of external intelligence systems, emphasizing the shared knowledge and collaborative frameworks that exist outside individual minds. It focuses on how collective intelligence found in cultural artifacts, digital networks, and social systems interacts with individual cognition to shape understanding and innovation. This approach highlights the mechanisms driving the accumulation, distribution, and evolution of knowledge within external systems, uncovering insights into how humans and technology synergize to solve complex problems and expand intellectual horizons. Case study: Meta-extelligence in open-source software development. Meta-extelligence is demonstrated in open-source software development platforms like GitHub, where collaborative frameworks enable collective knowledge creation and problem solving. Developers contribute code, share insights, and refine solutions within a shared digital repository. This external intelligence system, comprising tools, documentation, and community interactions, enhances individual and group innovation. By analyzing how these shared resources evolve and interact, meta-extelligence reveals the mechanisms driving the growth of collective technical expertise and innovation in software engineering. Meta-trade refers to the higher-level analysis and understanding of trading systems, focusing on the underlying frameworks, patterns, and mechanisms that govern trade activities. It examines how different factors such as market structures, regulations, technological advancements, and global interactions influence trading dynamics. By adopting a meta-level perspective, one gains insights into optimizing trade practices, addressing systemic inefficiencies, and fostering sustainable and equitable trading systems. This approach is particularly valuable for navigating the complexities of modern global trade networks and financial markets. Case study: Meta-trade in cryptocurrency markets. Meta-trade is evident in cryptocurrency markets, where the underlying frameworks, such as blockchain technology and decentralized networks, shape trading dynamics. For example, platforms like Ethereum provide smart contract mechanisms that automate trading processes, ensuring transparency and reducing reliance on intermediaries. By analyzing these meta-level structures, traders and developers optimize strategies to address scalability, security, and volatility challenges, driving innovation and efficiency in digital asset trading ecosystems. Meta-total refers to the holistic analysis of systems or frameworks by considering all interconnected elements and their interactions as a unified whole. It emphasizes understanding the comprehensive structure and dynamics rather than isolated components, aiming to capture the essence of how the system operates collectively. This approach is valuable in fields that require systemic thinking, offering insights into how various parts converge to influence outcomes, drive processes, and shape the functionality of the overall system. Case study: Meta-total in urban planning. Meta-total is applied in urban planning when cities are designed by considering all interconnected systems, such as transportation, housing, utilities, green spaces, and community needs, as an integrated whole. For example, smart cities like Singapore use comprehensive data analysis to coordinate these elements, ensuring that development balances efficiency, sustainability, and livability. By analyzing how all parts interact collectively, this holistic approach fosters cohesive urban ecosystems that address both present demands and future challenges. Meta-maxims refer to overarching principles or guidelines that govern the application and analysis of meta-level concepts across various domains. They emphasize the fundamental rules or philosophies that shape the exploration and understanding of underlying frameworks, mechanisms, or interactions. These maxims serve as a foundation for conducting higher-level analyses, ensuring coherence, adaptability, and innovation while addressing complex systems or abstract ideas in a structured and meaningful way. Case study: Meta-maxims in AI ethics. Meta-maxims are applied in the development of ethical guidelines for artificial intelligence. For example, overarching principles like transparency, accountability, and fairness govern how AI systems are designed and deployed. These maxims ensure that AI operates responsibly, avoiding bias and protecting user privacy. By applying meta-level rules, organizations create frameworks to address complex ethical challenges, fostering trust and innovation in AI technologies. This structured approach highlights the importance of universal guiding principles in navigating multifaceted domains. Meta-recursive refers to the analysis of systems or processes that self-reference or incorporate feedback loops at multiple levels. It focuses on understanding how recursion operates within frameworks, enabling structures to adapt, iterate, or evolve based on their own outputs. This perspective helps uncover patterns, optimize processes, and improve the functionality of self-sustaining systems, driving advancements in areas like computer science, linguistics, and complex systems theory. Case study: Meta-recursive in machine learning algorithms. Meta-recursion is utilized in machine learning algorithms, such as those for neural networks. For instance, backpropagation involves recursive feedback loops where the system continuously adjusts weights and biases based on errors from previous outputs. By analyzing these recursive processes, researchers refine the algorithm to improve accuracy and efficiency. This self-referencing approach is pivotal in optimizing models for complex tasks, like image recognition or natural language processing. Meta-completion refers to the analysis and understanding of how systems, processes, or frameworks achieve their final states or outcomes. It examines the mechanisms, patterns, and external factors involved in reaching completion, focusing on the interplay between components and the overarching goals. By adopting a meta-level perspective, insights can be gained into optimizing processes, addressing inefficiencies, and ensuring more effective and streamlined pathways to achieving intended results. Case study: meta-completion in hardware manufacturing. Meta-completion is exemplified in hardware manufacturing processes, such as semiconductor production. By analyzing the end-to-end workflow from raw material sourcing to wafer fabrication, assembly, and quality testing, manufacturers identify inefficiencies and optimize production. For instance, advanced monitoring systems track how each stage contributes to the final output, ensuring alignment with performance and cost objectives. This meta-level understanding refines the entire manufacturing process, enhancing precision, scalability, and product reliability in cutting-edge hardware technologies. Pragmatic meta focuses on the practical application of meta-level analysis to solve real-world problems and enhance decision-making. It emphasizes actionable insights, integrating theoretical frameworks with functional approaches to address specific challenges. By bridging abstract concepts with tangible outcomes, pragmatic meta ensures relevance, adaptability, and efficiency across various fields, such as business strategy, technology development, and policy implementation. Case study: pragmatic meta in disaster response. Pragmatic meta is exemplified in disaster response strategies, where abstract planning frameworks are applied to real-world scenarios. For instance, during bushfires, emergency services use meta-level analysis to integrate weather data, resource allocation, and evacuation plans into actionable protocols. This approach ensures decisions are both theoretically sound and practically effective, enabling rapid responses and minimizing harm. By focusing on pragmatic outcomes, the meta-analysis becomes compelling in addressing urgent and complex challenges. Meta-piece involves the systematic analysis of multi-layered frameworks and mechanisms aimed at establishing and maintaining conflict resolution, equitable governance, and sustainable coexistence. It encompasses the study of dynamic interactions among geopolitical structures, cultural paradigms, economic systems, and environmental policies. By leveraging advanced modeling techniques and algorithmic approaches, Meta-P seeks to identify systemic inefficiencies and propose optimized strategies for mitigating conflicts. This technical perspective supports scalable and data-driven methods for fostering long-term stability, emphasizing metrics such as socio-political resilience, resource allocation efficiency, and networked cooperation. Case study: meta-diplomacy in trade agreements. Meta-diplomacy is demonstrated in negotiating comprehensive trade agreements, such as the Regional Comprehensive Economic Partnership (RCEP). This involves analyzing and aligning economic, political, and cultural frameworks across multiple nations to foster cooperation and mutual benefit. Advanced meta-level strategies, including predictive modeling of economic impacts and scenario planning, support balanced outcomes by addressing systemic disparities. By leveraging such meta-diplomatic approaches, countries achieve long-term stability and strengthen international relationships through equitable and sustainable trade practices. Borderline meta explores the transitional or liminal spaces between distinct systems, frameworks, or concepts. It examines the interactions, tensions, and overlaps at the boundaries where different domains converge or blur. This approach seeks to uncover new insights, hybrid structures, or emergent phenomena by analyzing the dynamics of these in-between areas. Borderline meta is often applied in interdisciplinary fields, creative innovation, and systemic problem solving to leverage the potential of intersections and redefine conventional boundaries. Case study: borderline meta in seismic moment tensor analysis. Borderline meta is exemplified in the study of seismic moment tensors, which analyze the transitional dynamics between tectonic stress and fault rupture. For instance, researchers use tensor decomposition to explore the boundary interactions between isotropic and deviatoric components during mining-induced seismic events. By examining these liminal spaces, scientists uncover hybrid mechanisms like closing crack and double couple processes, which provide insights into the physical source dynamics of seismicity. This meta-level approach refines our understanding of fault mechanics and enhances predictive models for seismic activity. Meta-Revolver examines iterative frameworks or cyclical processes that enable systems or concepts to reset, adapt, or evolve through continuous loops. It focuses on the dynamic patterns of recursion and renewal, analyzing how outputs feed back into inputs to drive system transformation or sustain functionality. This approach is applied in fields like algorithmic design, systems biology, and iterative development, providing insights into optimization and adaptability in complex, self-sustaining environments. Case study: Meta-Revolver in genetic algorithms. Meta-Revolver is applied in genetic algorithms, where iterative processes evolve solutions to optimization problems. For example, in robotic design, genetic algorithms use cycles of selection, mutation, and crossover to adapt designs based on performance evaluations. Each iteration refines the population of solutions, feeding results back into the system for continuous improvement. This meta-level approach ensures adaptability and convergence toward optimal designs in complex, dynamic environments. Utopia is a meta-utopia, the environment in which utopian experiments may be tried out, the environment in which people are free to do their own thing, the environment which must, to a great extent, be realized first if more particular utopian visions are to be realized stably. Robert Nozick. Conclusion: the transformative power of meta-thinking and future horizons. The exploration of meta within the introductory meta course for the J.O.L.A.L.F reveals a profound conceptual framework that transcends disciplinary boundaries, offering tools to dissect, refine, and innovate across fields as diverse as philosophy, science, technology, and art. At its core, meta represents a recursive leap, a higher-order interrogation of systems, narratives, and knowledge itself. By dissecting its applications from Gödel's incompleteness theorems to agile software development, we uncover a universal truth: meta-thinking is not merely analytical but transformative, enabling societies, technologies, and individuals to evolve through self-awareness and adaptability. Advanced insights: beyond recursion to integration. Meta-learning and AI's frontier. The rise of artificial intelligence epitomizes meta's potential. Meta-learning algorithms, which optimize their own learning processes, exemplify how systems can transcend static programming. For instance, neural networks employing backpropagation iteratively refine their parameters, mirroring the meta-revolver concept. Future advancements may see AI systems conducting meta-analyses of their ethical frameworks, autonomously addressing biases in training data or prioritizing sustainability. However, this raises critical questions: can machines achieve genuine metacognition, or will they perpetually simulate self-awareness? The intersection of metaphilosophy and AI ethics will shape answers, demanding rigorous frameworks to ensure transparency and accountability. Meta-science and the crisis of reproducibility. While meta-analysis synthesizes research, meta-science, the study of scientific practices, confronts systemic flaws. The replication crisis underscores the need for meta-level scrutiny of methodological rigor, publication biases, and incentive structures. Advanced meta-scientific tools, leveraging AI to audit experimental designs or detect p-hacking, could restore trust. Yet, this requires a cultural shift, embracing metacritical peer reviews and valuing negative results as much as breakthroughs, fostering a science that is as self-correcting as it is innovative. Metafluidity in global systems. Climate change and geopolitical instability demand metafluid approaches. Urban planning case studies demonstrate how holistic, adaptive systems integrate environmental, social, and economic variables. Similarly, meta-diplomacy in treaties like the RCEP employs predictive modeling to balance competing interests. Future applications could deploy metafluidity to manage resource scarcity, using dynamic models that simulate ecological, economic, and societal feedback loops in real time, preempting crises through anticipatory governance. The ethical paradox of metadata. As metadata underpins everything from healthcare to digital advertising, its ethical implications grow urgent. Synthetic meta in advertising algorithms optimizes engagement but risks manipulative exploitation. Conversely, metacorrection in healthcare, e.g., adaptive error detection in patient data, saves lives. The challenge lies in governance, developing global standards for metadata usage that prioritize equity without stifling innovation, a balance akin to the meta maxims guiding AI ethics. Quantum meta and the limits of knowledge. Quantum computing's rise introduces quantum meta, where algorithms optimize qubit interactions and error correction. This mirrors J.O.L.A.L.F's revelation that systems cannot fully self-validate, posing philosophical and practical dilemmas. Can quantum systems achieve self-correction, or will they too face incompleteness? The answer may redefine computational boundaries, influencing cryptography, material science, and our understanding of reality itself. The J.O.L.L.A.L.F framework, synthesizing metadisciplines. While the acronym J.O.L.L.A.L.F remains undefined, its meta-course structure suggests a multidisciplinary crucible for cultivating meta-literacy. By integrating modules on meta-theory, metadata, and meta-narratives, the framework likely aims to produce thinkers who navigate complexity with agility. Future iterations could expand into metaethics, exploring how values emerge and evolve within systems, or meta-collaboration, enhancing human-AI synergies. Conclusion: the meta-imperative. In an era of exponential change, meta-thinking transitions from academic curiosity to survival skill. It equips us to deconstruct crises, innovate responsibly, and discern patterns in chaos. The J.O.L.L.A.L.F course, through its recursive pedagogy, models this imperative, challenging learners to not only understand the world but to reimagine the frameworks that shape it. As we stand at the nexus of quantum computing, climate upheaval, and AI revolution, meta-literacy becomes our compass, guiding humanity toward a future where knowledge is as adaptive as the systems it seeks to master. Final questions. Below is a list of 50 final questions for the introductory meta course for the J.O.L.A.L.F. These questions are designed to assess a deep understanding of the course material, encourage critical thinking, and prompt students to synthesize concepts across the various modules: foundational meta-concepts, meta-narratives in creative media, meta-analysis and meta-science, meta-theoretical frameworks, and metadata and metagaming. The questions span theoretical, practical, and interdisciplinary applications of meta-concepts, reflecting the course's goal of developing a rigorous understanding of meta as a recursive, higher-order analytical construct. Final questions for the introductory meta course for the J.O.L.A.L.F Module 1, Foundational Meta-Concepts. How does the etymological evolution of meta from ancient Greek to modern usage reflect its conceptual development across disciplines using set theory, Formalize a definition of meta as a recursive construct and explain its implications for self-referential systems. How can type theory be applied to distinguish between object-level and meta-level analyses in a formal system? What are the limitations of applying reflexive analysis to personal cognitive models, and how might these be addressed? Synthesize a logical deduction that defines meta in the context of hierarchical knowledge structures. Module 2, Meta-narratives in creative media. How does the use of fourth wall breaches in media, such as in If on a Winter's Night a Traveler, exemplify meta-narrative techniques? Apply a structuralist framework to analyze a meta-narrative in a film of your choice. What insights does this reveal about the medium? Using post-structuralist theory, deconstruct a meta-element in a piece of contemporary media. How does this challenge traditional narrative forms? Create a short meta-narrative that uses reflexive techniques to comment on the act of storytelling. What challenges did you encounter? How does semiotics enhance our understanding of self-referential signification in meta-narratives? Module 3, Meta-analysis and meta-science. Design a meta-analysis study to evaluate the effectiveness of a psychological intervention across 20 studies. What statistical methods would you use? How does meta-analysis address the issue of small sample sizes in individual studies, as seen in the antidepressant case study? Critically evaluate the epistemological foundations of meta-science in addressing the replication crisis in scientific research. Analyze the role of metadata in scientific data sets. How does it influence the reliability of meta-analyses? Perform a methodological critique of a scientific research paradigm of your choice. What meta-level insights can improve its rigor? Module 4, Meta-theoretical frameworks. How does meta-theory differ from traditional theory in its approach to analyzing social inequality, as discussed in the sociologist case study? Apply critical theory to deconstruct the assumptions of a theoretical framework in sociology. What biases are revealed? Compare and contrast two meta-theoretical paradigms in psychology. How do their epistemological foundations differ? Construct a meta-theoretical model for a theoretical system in economics. How does this model enhance understanding of economic behavior? What role does epistemological critique play in refining theoretical frameworks, and how can it lead to new theoretical perspectives? Module 5, Metadata and Metagaming. How does metadata in digital photography, e.g. EXIF data, enable forensic analysis, and what are the ethical implications? Analyze a metadata schema in a database of your choice. How does it support data lineage and integrity? Apply game theory to evaluate the meta in a competitive gaming strategy. How does this influence player behavior? Evaluate the sociological implications of metaverse architectures. How do they shape online communities? Analyze the impact of recursive online phenomena, such as viral trends, on digital culture. What meta-level dynamics are at play? Cross-module synthesis and application. How can the concept of metafluidity be applied to improve adaptive algorithms in artificial intelligence? Compare the use of meta in Gödel's incompleteness theorems with its application in meta-narratives in literature. What common themes emerge? How does meta-synthesis in qualitative research differ from meta-analysis in quantitative research, and what are the strengths of each approach? Using the case study of animal magnetism, explain how a meta-perspective can reveal the social construction of scientific knowledge. How can metatopology and metatypology be combined to analyze the structure and classification of social media networks? Advanced theoretical questions. How does metarealism address the tension between objective reality and subjective representation in scientific models of the atom? What are the philosophical implications of metateleology in evaluating the fine-tuning argument for the universe's design? How does the concept of metacognition in the brain relate to the philosophy of meta in self-referential systems? Analyze the role of metalanguage in resolving paradoxes like the liar paradox. What are the limitations of this approach? How does meta-externalism challenge traditional views of meaning and knowledge in linguistic theory? Practical and interdisciplinary applications. Design a meta-correction system for a wireless communication network. How would it adapt to real-time error patterns? How can metascattering principles be applied to improve the resolution of biomedical imaging techniques? Like OCT propose a meta-cloud strategy for a multi-cloud environment. How would it address scalability and cost efficiency? How can meta-diplomacy be used to negotiate a global environmental treaty? Considering economic and cultural frameworks, apply the concept of meta-revolver to optimize a genetic algorithm for a real-world problem, such as robotic design. Ethical and societal implications. What ethical challenges arise from the use of synthetic meta in digital advertising, and how can they be mitigated? How does meta-intelligence in open-source software development foster innovation, and what are the risks of knowledge monopolization? Evaluate the societal impact of meta-constants in fine-tuning arguments. How do they influence public perception of science and religion? How can meta-maxims guide the development of ethical AI systems, particularly in addressing bias and transparency? Analyze the role of meta-peace in fostering sustainable coexistence in a geopolitically unstable region. What metrics would you use? Future horizons and innovation. How might quantum meta-principles advance the development of quantum error correction codes in quantum computing? Propose a meta-microprocessing tool to explore novel computational paradigms like neuromorphic computing. What would its key features be? How can meta-fluidity be applied to address resource scarcity in the context of climate change? Provide a specific example. What role could meta-learning play in the future of AI ethics, particularly in ensuring accountability and fairness? Reflecting on Robert Nozick's concept of a meta-utopia, how can meta-thinking shape the design of future societal systems to enable experimentation and freedom? Reference and citation. References. Ayer, A.J. 1936. Language, Truth, and Logic. Victor Gollancz. Babby, E. 2016. The Practice of Social Research, 14th ed. Cengage Learning. Barths, R. 1977. Image, Music, Text. Hill and Wang. Battison, G. 1972. Steps to an Ecology of Mind, Collected Essays in Anthropology, Psychiatry, Evolution, and Epistemology. University of Chicago Press. Boghossian, P. 2006. Fear of Knowledge, Against Relativism and Constructivism. Oxford University Press. Bourdieu, P. 1990. The Logic of Practice. Stanford University Press. Calvino, I. 1979. If on a Winter's Night a Traveler. Harcourt Brace Jovanovich. Campbell, D.T. and Stanley, J.C. 1963. Experimental and Quasi-Experimental Designs for Research. Rand McNally. Chomsky, N. 1965. Aspects of the Theory of Syntax. MIT Press. Cochrane Collaboration. 2023. Cochrane Handbook for Systematic Reviews of Interventions version 6.4. Wiley. Cresswell, J.W. and Poth, C.N. 2018. Qualitative Inquiry and Research Design, Choosing Among 5 Approaches, 4th ed. Sage Publications. Davidson, D. 1984. Inquiries into Truth and Interpretation. Oxford University Press. Derrida, J. 1976. Of Grammatology. Johns Hopkins University Press. Eco, U. 1976. A Theory of Semiotics. Indiana University Press. Feyerabend, P. 1975. Against Method, Outline of an Anarchistic Theory of Knowledge. Verso. Foucault, M. 1970. The Order of Things, An Archaeology of the Human Sciences. Pantheon Books. Glass, G.V. 1976. Primary, Secondary, and Meta-Analysis of Research. Educational Researcher, 510, 328. https doi.org 10.31020013189x005010003. Gödel, K. 1931. On formally undecidable propositions of Principia Mathematica and related systems. Minutschrift für Mathematik und Physik, 38 1, 173-198. https doi.org 10.1007bf01700692. Hofstadter, Dr. 1979. Gödel, Escher, Bach, An Eternal Golden Braid. Basic Books. Kuhn, T.S. 1962. The Structure of Scientific Revolutions. University of Chicago Press. Lakatos, I. 1978. The Methodology of Scientific Research Programs, Philosophical Papers Volume 1. Cambridge University Press. Latour, B. and Wilger, S. 1979. Laboratory Life, The Construction of Scientific Facts. Princeton University Press. Lawton, L. 1977, Progress and Its Problems, Towards a Theory of Scientific Growth. University of California Press. Messmer, F.A. 1779. Memoir sur la découverte du magnétisme animal. Didot. Patterson, B. L. Thorne, S. E. Canham, C. and Gillings, C. 2001. Meta-Study of Qualitative Health Research, A Practical Guide to Meta-Analysis and Metasynthesis. Sage Publications. Popper, K.R. 1959. The Logic of Scientific Discovery. Hutchinson. Quine, W.V.O. 1953. From a Logical Point of View, 9 Logico-Philosophical Essays. Harvard University Press. Rorty, R. 1979. Philosophy and the Mirror of Nature. Princeton University Press. Saussure, F.D. 1916. Course in General Linguistics. McGraw-Hill. Searle, J.R. 1995. The Construction of Social
Yo, experimental music, what the hell is that? Like a grown man rocking pigtails in the back, and that's a compliment, just being honest. Soundtrack to the rest of the shit I'm talking. Said experimental music, what the hell is that? Like a grown man rocking pigtails in the back, and that's a compliment, just being honest. Soundtrack to the rest of the shit I'm talking. And now it's time to cut the ribbon. The mystery of rap, that's meta in description. The first rule of meta rap, no explicit mention. Illusion is the only form to give it recognition. Experimental music, what the hell is that? Like a grown man rocking pigtails in the back, and that's a compliment, just being honest. Soundtrack to the rest of the shit I'm talking. I said experimental music, what the hell is that? Like a grown man rocking pigtails in the back, and that's a compliment, just being honest. Soundtrack to the rest of the shit I'm taught to make my mama proud. Turned out I ain't shit. Spent my early years trying to get someone to pay attention. Finally learned that the thing you search for hours in the searching, unpredictable trajectory in this dimension. And the more I tried to grasp it, the further that it went. By the time I thought I got it, it left as fast as it came. As a kid, I had a passion for listening to things. My first words, experimental music, what the hell is that? Like a grown man rocking pigtails in the back, and that's a compliment, just being honest. Soundtrack to the rest of the shit I'm talking. Said experimental music, what the hell is that? Like a grown man rocking pigtails in the back, and that's a compliment, just being honest. Soundtrack to the rest of the shit I'm talking. I was a curious kid with nothing to lose. Imagination ran wild with colorful views, full of ambitions and dreams and wonderful hues. I think of everything I did to come up. I was a curious kid with nothing to lose. Imagination ran wild with colorful views, full of ambitions and dreams and wonderful hues. I think of everything I did to come up.